This problem asks us, how many subintervals should we use when using the Simpson's rule approximation to the value of an integral that goes between 0 and 1 for this function that's given, 9e to the x squared, if we want our maximum error for this approximation to be less than 100,000th of a point? When we use the Simpson's rule approximation to the value of an integral, we have a formula that tells us what the maximum error can be. E sub s is less than or equal to some value k times some b minus a raised to the fifth divided by 180 n to the fourth. What do all these letters mean? K is some value such that when we take the fourth derivative of the original function, it's got to be somewhere in between positive and negative k. We'll dive more into that in a bit. A and b are the lower and upper bounds of the integral, and n is the number of subintervals that we're using in our Simpson's rule approximation. So our task is to take 4 derivatives of the function that we're integrating, 9e to the x squared. The first derivative is taking the chain rule, 9e to the x squared, and then we have to multiply by the derivative of that function that was in the exponent, which is just 2x. As we get ready to take the second derivative, we're not only going to have to use some chain rule, but we'll also have to use some product rule along the way. So it begins by taking the derivative of the first function and multiplying it by the second function just left alone. Remembering here that the derivative of the first function, e to the x squared, is e to the x squared times 2x, and then multiply by that second function as is, just a 2x. The second part of the product rule says to write the first function, just e to the x squared, and then multiply that by the derivative of the second function, which is 2. What we have here is a pretty wide expression, and we want to make it simple. So we'll do a quick algebra move in order to accomplish that. There are 2 terms that are inside of the brackets, and they both have a 2 times e to the x squared involved. So we can factor that on the outside, giving us now 18 times e to the x squared. And inside the brackets, we're left with 2x squared plus 1. This step of factoring out a 2e to the x squared is something that we'll do again. And it helps make this next round of taking derivatives just a little bit easier, because we can see very clearly what our 2 functions are as we prepare to take the product rule once again. So we'll start out leaving the 18 as a coefficient out front and focus on taking the derivative of the product of these 2 functions. Again, the derivative of the first function is e to the x squared times 2x, and we'll multiply that by the second function left alone, 2x squared plus 1, plus take the original first function, e to the x squared, and then we'll multiply that by the derivative of the second function. The derivative of 2x squared plus 1 is just 4 times x. We'll do another simplification here by factoring out a 2e to the x squared, the same as we did in the last derivative, so that our first term that's on the outside now is going to be 36 times e to the x squared, and on the inside we're left with the result. The first term reduces to x times 2x squared plus 1, and the second term only has a 2x that's left. By now we get the idea. We do some simplification, we take another round to get into our fourth derivative by doing some product rule and chain rule, and when we factor out here, only 1 e to the x squared can be factored out. We have 4x to the fourth plus 12x plus 3 inside the parentheses. And we're ready to try to find that value k to plug in to our formula for the error. Well, if we plug in 0, we're going to get a value of 0. When we plug in the other boundary at x equals 1, that must be our maximum value of k, which is 36 times e times 19 which is 684 times e. And now we have all the values that we need to plug into the function e sub s. A reminder that it's k times b minus a, which is just the bounds of integration, raised to the fifth divided by 180 n to the fourth. So we have 684e, basically times 1, divided by 180 times n to the fourth. And our goal, remember, is to get that to be less than 1/100,000th of a point. Basic algebra will carry us the rest of the way now. We can multiply both sides of this equation by n to the fourth. And then with just a little more algebra, we get that n must be greater than 31, which we then have to round up to be 32, the number of subintervals that'll get our error just where we want it.